Let's continue now with the notion of a matrix representation of a linear transformation. And we'll start with an example. Consider the map from R2 to R3. We'll call it L, and L is defined as follows. L sends xy to 2y, x plus y, negative 3x. Then L is a linear map, and you can and should check this for yourself. Verify the properties A and B as we presented them in the original video. That is, that L preserves both vector addition and scalar multiplication. So what's next? Let A be the 3 by 2 matrix with rows 0, 2, 1, 1, and negative 3, 0. And we'll see that this linear map L and this matrix A are very closely connected. To see why, let's take the matrix A and matrix multiply it on the right by a column vector xy. So then we get this matrix product right here, and when we take the product of these two matrices from here to here, we get a 3 by 1 column matrix, 2y, x plus y, negative 3x. But that's precisely what we obtained when we evaluated L at the column matrix xy. So it looks like if we're starting out with a column vector xy, we can do two things. One, we can stick it in L, or two, we can matrix multiply it in front of A, and we get the same thing either way. So in this sense, it seems that L is given by a matrix, or L is represented by a matrix. There is some matrix out there, namely the matrix A, which does the same thing as applying the function L. But the function L does it by, well, evaluation of the function, and the matrix A does it by matrix multiplication. Here again is all we're saying. Sorry for the repetition. L evaluated at xy is the same as A matrix multiplied by xy. So by now you should be wondering how we came up with the matrix A. And I'd like to tell you that right now. So let's do the following thing. We have the linear function L, the linear map which we defined above. Let's take that linear map and evaluate it at the natural basis vectors of R2. If we do that using the recipe of L, it's easy to see that L of the basis vector 1, 0 is 0, 1, negative 3. And L of the basis vector 0, 1 is 2, 1, 0. So now let's take those vectors and line them up as column vectors. Here's 0, 1, negative 3, and here's 2, 1, 0. Here they are. And of course, what you've probably noticed by now is this is precisely the matrix A that we introduced above, or the matrix that represented or that represents the linear map L. If you didn't quite see how that correspondence worked, that's all right, because I'm going to write it down as a theorem right now. So here's the theorem. So we start with an arbitrary linear map from Rn to Rn and call it L. And then we take the natural basis of Rn. Remember, that's E1 is the vector 1, 0, down to 0. E2 is the vectors 0, 1, 0, down to 0, and so on and so forth. Ek in general is the column vector with 1 in the kth spot and zeros everywhere else. So we fixed L, we fixed this, the natural basis, and now we define a new matrix A as follows. Define A. So if you look here closely, we take the linear map L and evaluate it at D1, and then we stick that in as a column matrix. Then we take L, evaluate at E2, stick that in as a column matrix. Do the same thing all the way down the line, all the way down to En, evaluate L at En, and stick that as a column matrix. And then the theorem is that the matrix A represents the linear map L. That is, evaluating the function L at x is precisely the same as left multiplying x by the new matrix A that you have obtained. Let's look at an example. consider the linear map L from R2 to R2 given as follows. L of xy is equal to negative y, negative x. So, for example, L of the vector negative 2, 3 is negative 3, 2. Okay, and you could stick some other vectors in there to see what happens. And then you could also do the very important thing, which is to verify that L is in fact a linear map. It does preserve vector sums and scalar multiples. So the question, of course, now is that we want to find the matrix A that represents L. That is, we want to find the matrix A such that evaluating L and xy is the same thing as left multiplying xy by the matrix A. What should the dimension of A be? So you can actually figure this out by looking at the theorem above. So what do we have here? A should be a map, or A should be a matrix which, when multiplied on the right by an n by 1 column matrix, yields an m by 1 column matrix. So I should write up here that A is, or must be, an m by n column matrix to go from Rn to Rm. So right here in our example, our linear map goes from R2 to R2. So if we find a matrix representation of L, then it should be a 2 by 2 matrix. And that's also clear by the recipe for finding A. So let's find A. Remember what the theorem tells us to do. It says first go through and grab all of the natural basis vectors. For R2 there are only 2 of them, 1, 0 and 0, 1. And then we evaluate L at each one of those standard basis vectors. So L of 1, 0, applying the definition, gives us 0, negative 1. L of 0, 1, applying the definition, gives us negative 1, 0. And make sure you verify that for yourself. And so now we can build the matrix A. It is simply built by taking L evaluated at the first basis vector and sticking that in as a column matrix. L evaluated at the second basis vector and sticking that in as a column matrix. So here it is. A is equal to 0, negative 1, negative 1, 0. You can verify for yourself that L and A have the same effect. Let's go ahead and test it out on one vector. For example, let's take L of negative 2, 5. 1 second. There. What does L do to this vector? Well, remember, L sends xy to negative y, negative x. So it switches the components and flips their signs. So this should be negative 5, 2. Okay, there's L. Now, what happens when we left multiply this column vector by A? The vector, the matrix A that we found above. Well, that's what? 0, negative 1, negative 1, 0. Matrix multiplied by negative 2, 5. And if I carry out this matrix multiplication, I get precisely, remember, first entry is first row dot column, that gives me negative 5. And then second row dot column gives me positive 2, which is the same thing that we got by applying L. So A is indeed a matrix representation of L. I think I used this terminology above, but I failed to write it down. So let me record it here for posterity. If you fix first your linear transformation L and then build this matrix A as we described and as we did in the example, then we say that A is the standard matrix representing the linear transformation L.